rest of the subject, state estimation and discrete time linear dynamic system. Although before that there is a chapter, but that's not that much important, because we are interested for discrete time system. So before this there is a chapter for continuous time linear dynamic system, but continuous time system is not that much in used for the applications. We used discrete time system for state estimation and tracking purpose. So we are only taking this chapter and will study about the estimation algorithm for a discrete time linear dynamic system. So content of this chapter is linear estimation and dynamic system, where we study the common filter and we study how we can apply the common filter estimation for tracking some object, an example of a filter, then initialization of the state estimators and consistency of the state estimator. So in the first content we study about almost 8 topics. First we should understand the dynamic estimation problem. Then if we study about one cycle of estimating some point object, then how we can continue in a recursive manner, means we have to apply recursive mathematical equation so that automatically it applies the estimation algorithm repeatedly. So dynamic estimation is a recursive state estimation, and the derivation of the dynamic estimation algorithm, overview of common filter algorithm, the matrix Riccati equation, and the properties of the innovation and the likelihood function of the system model, innovation representation, and then the summary. So what is dynamic estimation problem? So these two equations are the model for any object tracking system. Okay, so consider the discrete time linear dynamic system described by a vector difference equation, all or vector, and this is equation discrete time. So we say that this is a object model equation, okay, object dynamic equation, or sometimes we just say the mathematical dynamic equation. So, and where Fk denotes the state transition. So Fk is nothing but is simply a matrix which involve the time, okay, and then this matrix is multiplied with the state of the object of any random parameter. This x is a random parameter. When this matrix is multiplied, then the next transition of the state will obtained, okay, as it contains the time, and this vector contains the two-dimensional position and two-dimensional velocity. So when it is multiplied with the time sequence, it will get the with the help of constant velocity model, it will help to calculate the next velocity which will add to the previous position. Then ultimately you can calculate the new position, okay. When this vector is multiplied with the this matrix, then the next velocity will be calculated, that will help to calculate the next position. So that's why we say that this is a state transition matrix. Xk is dimensional state vector with dimension nx. Uk is an dimensional known input vector. So Uk can have a control or control inputs, okay, or sensor platform motion. For example, in case of UAV, suppose UAV, so UAV control inputs may take uh, the thrust control input, okay, can have a thrust control input and or another control input to which controls the flight, okay. So this is a some control input or motion platform input or sensor input, okay. And Vk is the noise, is a sequence of zero mean white Gaussian noise. So Vk has a zero mean and the variance of Q, okay. The Vk is a white Gaussian with zero mean and the known covariance of Qk. Now the measurement. This is the sensor output. Okay, we call this the sensor model. Okay, we call this the sensor model which calculate the measurement. Okay, with the additive Wk noise. Okay, so Wk is a sequence of zero mean white Gaussian measurement noise. This is a sensor noise or position measurement noise. Okay, with known covariance Rk. So the both noise are uncorrelated to each other. They are independent to each other. Rk is a measurement noise, and the Qk is a plant noise. Is a model noise. Plant means the dynamic model noise. Okay, the dynamic model noise. Suppose this is dynamic model. So Vk is this noise, and Rk is a camera noise. Okay, so both are independent, and the measurement noise is added to the sensor measurement. Okay, and Hk is a measurement matrix. So measurement matrix is nothing but it's just select because this x is the position and velocity, so it just select the only position. Okay, so it is if it is 4 by 1 vector, then it will be 2 by 4 vector. So out of 2 by 4 vector, half side is the unity identity and half side is 0, so that when it multiplies this one, then it will select only the position. This output, this vector is a 2 by 1 vector, 2 by 1 vector. If you are tracking the object in the just two-dimensional surveillance region like x and y, then this will be 2 by 1 vector, and if we are tracking the object in three-dimensional, then this will be the 3 by 1 vector. So this will not select the velocity, this will select just position. And this is a next scan state value. Okay, clear?
What is mean about GK?
GK is a constant vector. GK is a constant vector. Okay, GK is a constant vector. It's multiply with the input. Is select the selective control input. Means what do you want to control? Which input do you want to use? This is a remote control. There are so many control input, but only at one time you can use one input. So it will select one input or two input to control the operation for the position tracking. Okay, and the K denotes the scan. Okay, at 0, 1, 2, 3 means 0 time. This will start from 0 time, and 1, 2, 3 up to the K is denotes the scan. So the matrices F, G, H, Q, R are assumed known and possibly time varying. In other words, the system can be time varying and the noise is non-stationary. The initial state x0 is in general unknown and is modeled as a random variable. When we start the problem, then we do not know the initial state of the random variable x, but it is modeled as a random variable and Gaussian distributed with non-mean and covariance. The noise Vk and Wk sequence and the initial state assumed mutually independent. The above constitutes called the linear Gaussian assumption, and the linearity in 1 and equation number 3 leads to preservation of the Gaussian property of the state and the measurement. This is called the Gauss-Markov process. This is called the Gauss-Markov process for the property of the state and the measurement. Now, following notation will be used. This is estimator, and this is the conditional mean of the state at a scan k. Okay, and this is a expected value of the random variable condition on the zk. Okay, as you know, the zk is the complete set. Is a complete set which includes the zi, and I is the number of scan. So I and k is the last scan. So it's a complete set, and the small z is a part of this one. You can say the subset of the zk. So z1, z2, z3 up to zk is so as your estimator is expected is equal to the expected value of the random variable given the measurement set from initial time scan up to time k. Okay, means when you start the algorithm, sensor returns the measurement for all. It will not return just one scan. It will return you all scan from initial time up to time k. So zk is given observation up to and including time k, and k is the current scan. Okay, so this denotes the sequence of observation available at time k. Okay, now what does this mean? K condition of k. K condition of k is this one, that this is calculated value at the current scan. So what is the estimated value of the x at scan k given the k measurement? This k given the k scan, you have already a k scan. Now you are estimating the x of k. So it means you have already known the k, and you have already calculated the expected value of this one from initial scan up to the k. So estimate of the state k is called the filtered or estimated value denoted by the k, and the predicted value of the state at k plus 1 is called the state prediction or denoted by the bar. So if this is a predicted value, then it will be written as x k plus 1 given k, means given the current scan, given the k time scan measurement, you are predicting a time ahead k plus 1 times k. Then it will be called the prediction, state prediction. You are predicting the next scan estimated value, and this is the filtered value. And the estimation error is defined as this one. This is a notation for the estimation error at time k equals to the random variable, the problem parameter minus the estimated value. and the conditional covariance matrix of x of k given the data zk, or the covariance associated with estimator, is expressed in this. So the covariance is expression over the error, over the mean square error, So one part is with the transpose, and given the condition of the zk. So, or we can write here this equation, because this is same here. So this is the expression over the mean square error. So we can write this equation. We can express the covariance either in this way or in this way. Both are same. Okay. And we can note that the covariance of the state is the same as the covariance of the estimation error. Means the covariance of the state will be used for the covariance of the estimation error. When we calculate the estimation error, we can use the same covariance as that of the state covariance. Okay, so we know the dynamic equation, and we know the notation like this estimator notation, and sometimes we use cap over here, because this is also calculated as a estimation algorithm output, like Kalman filter output. So Kalman filter gives you output this value and this value. So sometimes in some book, in some papers, you can see the cap over here. So this is also the filtered value. This is also the filtered value at the output. So these are the notation. If there is a bar, then predicted value. If there is a cap like this, then this is the estimated or filtered value, and the covariance and the estimation error. Now the algorithm start with initial estimate this of true value of a random variable x of k. So x of k is your unknown variable, which is your object to find the parameter. X of 0 is a true value. So you have to assume that there is any initial estimate of this thing. Okay, and associated initial covariance of this thing assume to be available. But there is some formula to calculate this value. If it is not assumed, then it can be calculated. It can be calculated with the 2-point distance formula. Okay, 2-point distance formula. If you know the first position, then you can, if you know the first two position of the target, you can use the 2-point distance formula and divide by the time. So you can calculate the next third stamp position and the velocity vector. Okay. So again we said that this is the filtered value or updated value. So it is usually assumed to available, but if it is not available, and similarly at the same time covariance of this vector is 0, then it can be calculated, because this is the initial value. If you know the initial value, then you can apply the estimation algorithm to find the next prediction. If it is not available, then either you can use 2-point distance formula. If your problem has been given with the 2 position of the object, then you can use the 2-point distance. Okay, and or you can use 1 point. if your problem has been given to you with only one point, with only one value x of 0, then in this case you cannot calculate the velocity, but you can only calculate the position. Then you can use this thing in the estimation algorithm like Kalman filter to calculate the next position. So both are practical way to calculate the first position, and then using this you can apply the algorithm estimation algo to obtain the prediction. So normally this will like this one, k plus 1. This is a 0 times k, so k plus 1, or we can write here k plus 1, and similarly k plus 1. Then the cycle is repeat. Then this will be filtered to obtain the x filter value like k given k, and then again this is going to be prediction value, similarly continues. Okay, so filter value, the first filter value must be already known, and then you can find the prediction, then filter value, then prediction, then filter value in each step. So your algorithm will start with the initial estimate, which is assumed to be available, and the conditioning argument of 0 stands for z of 0. Okay, the initial information. The z of 0 means the initial information. First, the first measurement of the z. Now, this is called the practical procedure to obtain the initial estimate and the initial covariance. So this will be discussed later. How we apply the two-point distance initialization of the filter value, or one-point distance initialization of this filter value. This will be discussed in the later chapter. So one cycle of the dynamic estimation algorithm, for example that is Kalman filter, will thus consist of mapping the estimate of the given equation 5 This will map, because you already, the first value is assumed to be known. If it is not known, it will be calculated. So the Kalman filter will map this the estimator given in 5 and the associated covariance matrix given in 8 into a corresponding state prediction and state covariance at the next scan k plus 1, like this one. So it will map, the Kalman filter will map the given filtered value in 5 and 8 in the corresponding state prediction at the next scan k plus 1, denoted by this one. Okay, denoted by this one and this one, and this will use at the next scan to calculate the estimate for the next scan based on the next scan measurement. This follows from the fact that the Gaussian random variable is fully characterized by its first two moment. First two moment means mean and covariance. So we have to calculate the mean and covariance in each scan, and the values of past known. So suppose we are ignoring some notation for simplicity. The values of past known inputs are included in the conditioning. Okay, past known values are included in the conditioning, but most of the time will not be shown for the explicitity in this chapter. Now This is just one cycle. What about the next cycle? So it's a recursive state estimation. So what is the dynamic equation? Is a recursive state estimation. So the recursion that yields the state estimation a k plus 1 and covariance can be obtained from the static estimation equation like this and this. So your estimator has an expression of the x. We have ignored the variable which is inside the equation number 5 and 6 for simplicity. So this is equation is the expression x given. This is a z, which is a subset of the z power k, is equal to the mean of x and have covariance matrix. Okay, we discuss this in next slide. This is as a filter gain. Okay, and then it's multiplied by the z minus z inverse. So z is the same as this one. This is a sensor measurement. Okay, this same as this one, and this is the is from some estimated equation z mean. This is the mean value of the z. So as we have discussed in previous chapter that since z is a random variable, so this is also a random variable. So we have discussed the Gaussian algorithm, which is used for the random variable. So these two variables are almost same, because in some paper you will see here some publisher, some authors have written the same notation x bar and here x bar, because this is the same. This is equals to the estimator. This is equal to the estimator. So one can write the x bar, but in the book here written here this way, because to differentiate. So to differentiate, so there is some difference in this and this value, but one can write in this way. So this value is calculated based on the measurement. Again, you have to check the difference. So the value that you have calculated using any estimator to find the mean value of the z will then be will take some difference. What is the difference between the measurement set and the mean value of the z? Then it's multiplied with the filter gain and it's added to the prediction. Okay, and this is the same thing as this one. For example, okay, we have already assumed to available this thing. This is known at the 0 time scan. Then at time scan k, suppose any time scan k equals 2. Suppose we are here k equals 2. So at k we have to find the estimator value of 2 by 2, expected value of x z equals to this x bar is actually the k plus 1, because we have already calculated the filter value. This way filter value is used as here. What is the previous value? We have to propagate. We have to send this information to the next scan. So the next scan, the estimation, the Kalman filter should know what is the mean value of the x in the previous scan. What is the mean value of the x? The Kalman filter should know about the x. So what is the previous value of the x? So we have to send this information in the Kalman filter. to calculate the new value. So this is the periodic information of periodic state. Periodic state means that this value is previously known or previously calculated. Okay, and this value is the posterior or filter value. Means, and this value is calculated based on current scan Z. Okay, this value is calculated based on the expectation of x and z k plus 1. Means the z k plus 1 is the previous measurement. We can write here the minus 1, but for simplicity we are sending this information to next. Means if you have some information but you don't know, then you will have to forward that information. If you forward this information that you are adding information for the future time. Okay, so this will propagate it to the next time scan. So this notation will be converted like 0 plus 1, because we are sending this information from current scan to the next scan. Now, so the notation is changed. This is information is current scan. And again, how we transfer this information to here with the help of the state transition matrix. If we multiply this thing with this one, then it will transfer to the next scan. So this is called the prediction value. So same thing we'll discuss. And similarly, in the next time scale, this value will be used here to calculate the new value, and similarly continues like this one. And this is something covariance, the expression of the mean square error, condition on Z, and this is equal to Px and this thing. The proof is given in the book, and where the periodic available of the measurement at k plus 1. Okay, at k plus 1, for the we are sending the information. So this is called the periodic variable, periodic of the state availability of the measurement in k plus 1, that is given the measurement up to and including the k. So this information is given the up to and including time k in time k plus 1. And this estimator becomes posterior. This is a posterior value which will be used to obtain. This will be used to obtain the measurement in time k plus 1. And given the measurement up to including time k plus 1. So the posterior will be used to obtain measurement in k plus 1, which means that it will given the measurement up to and including k plus 1. The variable to be estimated is the state at k plus 1. Therefore, the state mean period to k plus 1 is called the one step ahead. Means the posterior posterior is the one step ahead. One step ahead means when we calculate the posterior variable, then we can therefore we can calculate the one step ahead value, means k plus 1. Now we are at the position of the k plus 1. So for example, this k indicates that the prediction bar k plus 1, which is given from the previous filter value, that like this one, the previous filter value. This is equal to this one, this which the first value of the estimate is assumed to known. So this is the same as this one. Condition on k, because it was calculated based on the k. It was calculated based on the k. For example, in case of this estimator 0, condition of 0, it was calculated based on the z power 0. And here's the expression is equal to expression of the k plus 1 condition of zk. So based on the observation measurement zk plus 1 with the period mean the predicted measurement, where the zk indicates that the zk plus 1, the previous value, is equal to same value, because we are using the previous information here to calculate the new information as the expression over this one. Clear? I have already discussed this thing here, because the comma filter must use the periodic information of x and the z mean to calculate the new information. Okay, clear? Are you sure? Clear? Okay. You? What you? Little. Okay, little. The updated step estimate posterior to k plus 1 becomes this indicates that k plus 1 equals to k plus 1 condition of k plus 1. Okay, so for example, this is time 1, 2, 3, 4. Okay, and this is x, the position of a state variable like k. Suppose some point object is moving here. Now we have to at first we do not know any variable, so we have to assume that there is a target having value this one. We have to assume this value to be known, so we have to calculate using 1 point if 1 point is given, or 2 point if 2 point is given. If 1 point is given, then this is your filtered value like 0, 0, having a covariance 0, 0, having the z mean 0, 0. Okay, this is the measured position, this is covariance, and this is filtered value or estimator. This is measured position is from the estimator, like maximum likelihood estimation or least square or maximum likelihood estimation, where we apply in both estimator we apply the maximum likelihood. So you can say that the measured position is the output of the maximum likelihood equation. So at first we have to know or calculate using this one. Then we can propagate, we can predict. First, propagate means prediction. Propagate means prediction. When we predict here this one, then this will be like this one. In second time scale, this will be 0 plus 1 given 0. Given 0 means we already know the value, we already know the assumed value or calculated value at here, and now we have prediction this time for the next time scale. K plus 1 given k, k plus 1 given k means the k this k is previous one, and this is the prediction. Similarly, P0 plus 1 given 0, and similarly Z mean, you can write here is a prediction here, because in the publication people write this notation for simplicity, so that they can know that which one is the filtered value and which one is the prediction. So 0 plus 1 given 0. Then this will be used in the equation number 5 and 8 to calculate the filtered value of the estimator and its covariance. Okay, so here we will find that k plus 1, k plus 1, k plus 1. Why? Because the new filter value is at 1 plus 2, 1 plus 2. We are here, we are not here. So we will use this zk plus 1 or which is nothing but z of 2. So we have to write this, because this is new value is calculated for the this time scale measurement. This is not condition to the previous scale, but this is a condition on previous scale, because this is calculated in the here. This is calculated from here. Now for the new value, we have to use the measurement of the new scan measurement. So this estimator k plus 1 and okay. So you have to note that the periodic mean predicted measurement indicating z k plus 1 prediction, because we are sending the information to the next scan, is calculated using the likelihood function, whereas the step periodic mean including this information is calculated by the estimation equation like Kalman filter. And the periodic covariance of the state variable at k plus 1 to be estimated or to be filtered using Kalman filter to be estimated. The state prediction covariance or predicted state covariance is this one. So Pxx stands to covariance. This means the prediction covariance, and the next is k plus 1 means this one. This is the predicted value which is coming from previous scan as the covariance of this thing, conditioning of the zk, and which have a covariance because this covariance have an expectation over the mean square error. So we can write directly this sign. This is the estimation error. We have the last quantity following from the equation number 8. Okay, so Px is the predicted covariance. Pzz, the periodic covariance of the observation zk plus 1, the measurement predicted covariance. The Bzz is the predicted covariance of the z, which we denote in the algorithm with the help of s. We denote this thing with s, okay, and it's equal to the expression of the z at k plus 1 given the zk and having the covariance this one. Now this is covariance between the variable to be estimated between the k plus 1, x of k plus 1, and the observation k plus 1. Means cross covariance of the x and z. This is also the prediction. Okay, this is also prediction, cross covariance of the prediction and having the covariance of this one. And similarly, Pxs Z is the posterior covariance of the state k plus 1 or that is the updated state covariance, this one. Like this one, in the scan time 2 we have to calculate k plus 1 for the new measurement set, that is k plus 1, and having the covariance of this one, this thing. Here we write k plus 1 because we are currently to another scan, the posterior scan, and to calculate the posterior x covariance, and having the covariance matrix like this one. Okay, so you have to remember the notation that we will use. Updated state of filter value as a cap, and the prediction have a bar sign, and similarly periodic mean measurement has a z and bar, current scan, and the prediction state k plus 1. Clear? Any question? Now this equation that we have used here, this is the filter gain or the weighting matrix, which is multiplied to the z minus z mean. From the estimation updating equation 9 becomes the filter gain. Okay, this equals to, we denote it with the w k plus 1, having the covariance of z and k, because the cross correlation x and z, okay, x and z given the zk, and this thing is a s of k plus 1. This thing is a k plus 1. This thing is we already denoted s, and this is the cross correlation. Cross covariance, and s of k plus 1 inverse is the covariance of the predicted mean measurement. The reason for designation of the above is a filter gain are as follows. The recursive estimation algorithm is a filter. It reduces the effect of the various noises on the quantity of the interest, like state estimate. It reduces the effect of the noise from the state estimate. So the quantity 18 multiplies the observation z plus 1, which is the input to the filter. So this quantity is called the gain. So this illustrates the tracking of a moving point, like this one figure, the flow chart and the figure. So assume there is some point distance, any point is moving, and you are tracking the one point. Like this, I already explained. So graphical state estimation process for a point moving with the nearly constant velocity along the x-axis. The state vector consists of position x and velocity x dot with estimate x cap and x dot cap respectively. The covariance matrix of the state is denoted by P, and it indicates the uncertainty region around the estimated state. So our measurement set is this one, and the new position will be, here we have not written the f because only one side, okay, only one side we do not know velocity. The new position will be between the observed and predicted value. Suppose the new value is between this one and this one, okay, the new position that will be estimated between the observed and predicted values. So this is the flow chart to calculate the variance. So both are calculated together. correspondingly. So this is the variance of the state. This is the corresponding covariance of the state estimate. So both follows together. So state estimate to be already assumed to be known, okay, and this will propagate to the predicted state k plus 1, because to calculate the new estimated value, the new scan must know the periodic information. So first we have this as assumed to be known, and then it will be propagated to the next scan, so that new filter value will be calculated. And the predicted measurement, this is also propagated from the assumed value, and then this is a new measurement set, new measurement set, okay, and state estimate. So for the calculation of the new state estimation, so this sign is like this minus sign. Minus means the previous value has been sent to the next scan, okay, so that's why it's minus. Okay, we have sent the periodic predicted, we have sent the periodic information as the prediction at the k plus 1, and when new scan measurement is inputted to calculate the state estimate, then this information is used. Okay, the state prediction x mean and z mean will be used to calculate the new state estimate, and the filter gain here. Okay, and this is the same thing. So this is a sequence of operation in the common filter. Okay, clear? And again, this is the same thing that I have explained. So if you have any question, so here this line is a trajectory of the moving point. This is the first scan, this is the next scan, okay. So position estimated, this position is assumed to be already known, and so that we can calculate the other thing. So this is the position, and this is the velocity of this position is assumed to be known or calculated, having the pk covariance. So in this case we can say that this is the filter value, and now the another value we can say that our point target is here, but this is the new position. Suppose the new position is between the measured position and the predicted position, although there is some difference because of the covariance, because of the error, there is always error. So the new position measurement is between the measured position and the predicted position, and having the velocity here and here, and this is covariance here. So the new position will use this value, and this value to calculate this value. The new position will use this value, and some gain like the covariance pxz and pzz to calculate the new position. Okay. Now we shall end this class here, and we will continue in the next week. Any question you can ask. Okay, so you can stop the recording.